All right, let's go ahead and get started. Let's see. I want to start by putting something on the board here, and I'm going to suggest that you guys write it down. This is for homework 8, number 16. Because I don't think I'm going to get there in class today. We are eventually going to see that enthalpy is defined as the energy of the system plus the pressure times the volume, right? That's a definition, and we'll show where that comes from and why we use it down the road. What I can do is I can say then that delta H is equal to delta U plus delta P times V. That makes sense to everybody? All right. And then because we're talking about ideal gases, we know that P times V is the same as, do you guys know? P nRT. Look at that. That's awesome. What grade are you in? Senior. All right. All right, so we can say that delta H is delta U plus the change in nRT. And if we're holding the number of molecules or moles of molecules constant, that means that's going to be able to be pulled out in front of the delta, so it becomes nR delta T. All right, so you need that for the last question on homework 8. Okay? Any questions about that? Okay, so very quick overview. So there's extra credit opportunities. You should have received emails to do evaluations for Melissa, Brian, and myself. If you complete all 3, you'll get an extra point added to the exam 2 score. Please be aware that I can't change the due dates. I can't look at what you've submitted. So it's completely anonymous. Please give us, constructive feedback. Let us know how we can improve, or if we're doing something right. The deadline for completing that is this Friday at midnight. I can't alter that. I have nothing to do with administration of this. Right? The only thing I know is I can get an email that says these people have completed it. All right, so exam 2 is next Tuesday. Study materials are posted. Friday we'll have our first review session. I have an unavoidable all-day conflict on Friday, so Brian's going to be teaching class at 10. Right? And then come prepared to the review sessions. All right, so one of the handout that I've given you today has 2 copies of this figure on it. And we're going to be spending a lot of time talking about this. So you want to be familiar with it, and it is covered on exam 2. Right? So we're basically looking at pressure versus volume. So far, we've talked about isothermal expansion and compression. So the way that I know that this is isothermal is I see that T1 and T2 are the same. All right? So we're going to be talking about that path. We know that the temperature is not changing. So what can you say about delta U for that path? What's the change in the energy for our system? It's got to be 0 because U is a function of temperature and number of particles only. If I'm holding the number of particles and the temperature constant, delta U has to be equal to 0. Right? Now, one of the things that we're going to be showing is that if we go from here to here via different paths, we would expect that we're going to have delta U the same, because we know that the energy of the system is a state function. So going from here to here, here to here, that delta U for that process we expect to be 0. Does that make sense? Okay? All right. So then in perspective, let's just talk about a few things. What we're going to cover today is an adiabatic expansion. So one of the things that we said last time was that if I do an isothermal expansion, I'm expending energy due to the expansion. The system's doing work on the surroundings, right? In order for the system energy to stay constant, that means that I have to absorb exactly the same amount of energy as heat from the surroundings. Right? So if I think about doing an expansion where I don't let heat transfer, where Q is equal to 0, that tells me that in expanding, I'm decreasing the energy of the system, and I can't compensate by absorbing heat from the surroundings. So what has to happen to the temperature of the system? It has to go down, right? Because my energy is my system is expending energy. but it can't absorb anything. Does that make sense? So for this adiabatic path, we see a decrease in the temperature. All right? So we're going to talk about the adiabatic path, and then we're going to talk about going from this point to this point. What's being held constant going from here to here? Path C. It's the volume being constant. So what, if we think about heat and work, which of those two terms is going to be equal to 0 for that path? Work, right? Because we can't have expansion or compression. The volume is constant. So this basically means that I'm heating the system at constant volume, right? Homework number 9, the one it's currently posted, is due next Friday. Questions 1 through 5 are covered on the exam. It steps you through it. It sounds like a lot, but it really steps you through it. It's basically looking at this path followed by this path, right? And you already know that delta U for this path from here to here to here is going to be 0, right? Because it's a state function. But you need to look at heat and work transfer and heat and work transfer. We're holding volume constant. I'm going from this temperature to this temperature. If going from here to here represented heating at constant volume, going from here to here has to be cooling at constant volume. Work will be equal to 0. This corresponds to be holding pressure constant, so that's a constant pressure heating process. Okay? Does that make sense? All right. So previously, what we've discussed, we've defined work as the negative PDV. We know that we can integrate it. We're going to be talking about work for ideal gases. We've talked about the energy of our ideal gas system being a function of the number of particles and the temperature only. So if I hold temperature and particles constant, it's going to be equal to 0. And then if I want to know what delta T is, we know that we can go to the heat capacity, which is by definition du dt, right? And so I can rearrange that and say du is equal to the heat capacity dt, and I can integrate that, right? Okay, so we've also looked at expansion, talked about the sign conventions. So if my system expands against an external pressure, I'm expending energy. Therefore, from the system perspective, work is negative. If I compress, that means that the work is positive. We've calculated work for single step expansion, compression, multi-step expansion, compression. We've talked about them. We've seen that if we do it in multiple steps, we get more work out of the system by breaking it up into steps. I also minimize the amount of work I have to do on the system to compress it by breaking up into multiple steps. And then we basically use this to argue that if I break up the steps into an infinite number of steps, each change in pressure is infinitesimal. That's a reversible process. And that maximizes the work out of the system and minimizes the work that I have to put into the system in order to do a compression. All right? We're going to be talking about delta U for the isothermal process again today, and then adiabatic process is all we've said about it up to this point, is that there's no heat exchange between the system and the surroundings. Okay? So things that we want to talk about. We've already determined that if I do an adiabatic expansion, I'm expending energy. The system energy is decreasing. I'm not absorbing heat to compensate, so the temperature has to go down. We're going to see explicitly what that temperature, that final temperature will be relative to the initial temperature, right? The other thing that we know is that when we've seen isotherms, we know that that function, that curve, is PV equals a constant. So we want to know the function that describes the pressure-volume relationship for an adiabatic expansion. And then from there, we're going to take a slight detour and talk about statistical thermodynamics, looking at that and using that to talk about heat and work. And you may recall back in Chapter 3, we said that the pressure of a system in our ensemble is given by the change in the energy of the system due to a change in volume. We use that without saying where it came from. We're going to see where it comes from today. A couple things to think about. We have previously pointed out that our system energy is going to be the average energy of the ensemble of systems, and that's the summation for all of the possible quantum states for the probability of being in a quantum state times the energy of that quantum state. That gets me the average energy, right? And we're going to be using that as well, hopefully today. I will say that every step of the way today I've been behind, so we may end up that way today. All right. So we've talked about this graph a little bit. We're looking at this point. I'm going to call it A to B. We've determined that this path A is isothermal because we're going from T1 to T1. If I'm going in this direction, I'm expanding. If I go in this direction, I am compressing. Okay? We've established that because it's isothermal, the change in the energy of the system is equal to 0. And what we can say is that from the first law, the change in the system energy is given by the incremental change in energy due to heat transfer. We're going to choose the reversible process, plus the incremental change in energy due to reversible work. All right? Okay, now because we know on this path that delta U is equal to A, and if I'm performing it, or is equal to 0, because I'm performing it reversibly, I know that every step of the way this is equal to 0. And that also tells me that the heat transfer is exactly equal to the work transfer, but the opposite direction in terms of the joules. Right? So we can say that dW reversible is minus dQ reversible. And we have previously defined expansion and compression work as minus P dV. Okay? All right, so those guys are equal to each other. And then if I integrate that, I end up with the reversible work is the same as the negative of the reversible heat transfer, right? And that means that we need to integrate this, and previously we've integrated that and found that that's equal to minus nR ln V2 over V1. Okay? All right, so all we did was substitute in nRT over V integrated between V1 and V2, and that gave us the result. Okay? All right, and then if we're talking about an expansion, work is negative. And that's because our system is doing work on the surroundings. All right? And because there's no change in the energy of the system, that means that Q is the opposite sign. That means it's positive. And that tells us that the system absorbs heat from the surroundings. And that's what's necessary to maintain a constant temperature. Okay? Does that make sense? All right, so now what we want to do, and this is part of the reason I gave you the other figures. I'm going to go to the next page, and we're going to be talking about paths B and C. All right? So we've discussed Q and W and delta U for path A. What we want to do is compare that with Q and W and delta U for path B plus C. Okay? All right, so we've defined path B as adiabatic expansion, which means necessarily Q on that path is equal to 0. Right? We've established that the energy of our system depends upon temperature, and therefore we can go to the heat capacity and say du will be equal to Cv function of T dt. And if I integrate that, I end up with the change in the energy of my system is given by the integral from T1 to T2 of Cv dt. Okay? All right, so for what we are talking about, path B, we've established that the heat transfer is 0, all right? And what we can say is that delta U will be given by this integral T1, T2, CV, T, dt. And that in turn is equal to, help me out. No, it's not equal to 0 because we're doing adiabatic expansion. We know the temperature is going down, right? Q is equal to 0, so what's not equal to 0? Work. So that has to be equal to the work. Okay? All right, now if we talk about path C, we've already stated that along path C, we're holding the volume constant, which forces work to be equal to 0. And so this means that the only thing that I'm doing is heating the system at constant volume. Okay? So if we're talking about path C, work is equal to 0, so we can say delta U will be equal to Q reversible for path C, and that in turn we expect to not be 0 because we're heating the system, right? So that's going to be the integral of CV T dt, right? If we go back to the figure, what we see along path C is that we're going from T2 to T1. All right, so our limits of integration are from T2 initially to T1 finally. All right? So we've talked about the heat and work for each of the paths B and C. Right? So now what I want to do is just look at the total heat transfer for path B and C. That'll be Q reversible B plus C. Right? Well, for path B, it's adiabatic. What's the heat transfer? It's 0. All right? And then for path C, we've determined that it's this integral T2 to T1 CV T dt. All right? So that's Q reversible for path B plus C. We do the same thing, but now looking at work for path B plus C. All right? And for path B, the only energy transfer to our system is due to work, right? And so that's the integral from T1 to T2 CV T dt, right? And because we're holding the volume constant for path C, that means the work for path C is equal to 0, right? Now it's very clear that if I go back and compare this reversible heat transfer and reversible work transfer for path B plus C with A, we saw that that's equal to NR ln V2 over V1. That's not what I have here, right? Okay. I also want to talk about this from one other aspect. If we were to look at this graph and say for the isothermal process, how do I determine the amount of work? Well, we know it's the integral of this curve, right? So it's the area under here. So for the reversible expansion, this area underneath that is the work, right? It's also the heat absorbed because they're equal to each other, okay? If we look at the adiabatic process, it's pretty clear that the area under that curve is less. So the work is different, right? Does that make sense? Okay? So what we can conclude is that W reversible for path A is not the same as W reversible for path B plus C. Right? We can see that graphically and through our calculations. And the heat transfer for path A is not the same as the heat transfer for path B plus C. Right? And so what that tells us is that even though path B plus C, starting and end point, are the same as path A, I don't have the same heat transfer and I don't have the same amount of work. And that tells me that both heat and work are not state functions, but they're path functions. Okay? But we've also said that if we look at the change in the energy of the system, we expect that to be a state function, right? So for path B plus C, that's going to correspond to the total heat transfer on path B and C plus the energy transfer in the form of work. So this is delta U for path B plus C, right? And if I come up here and I say, all right, we know that our reversible heat transfer for the sum of those two paths is given by this integral, right? That's integral T2 T2 to T1 CV T dt. All right, so that's my first term. That's the total heat transfer for path B and C. And then I add in the energy change due to work. That's going to sum to the integral from T1 to T2 Cv dt. And what does that sum to? That sums to 0. All right. Now, just in case you didn't see that, right, what I'm going to do is say I'm going to change the limits. Instead of going from T1 to T2, I'm going to go from T2 to T1. Right? And in order for me to do that, oops, I didn't reverse it, did I? T2 to T1 Cv T dt. To make that equal to this term, what do I need to do? I need a negative sign in front of there, right? And so if you look at it from that point of view, it's pretty straightforward. This is exactly the same as this, so they have to go to 0, right? And that's what we showed was the same as delta U for path A, our isothermal process, right? So what we've demonstrated is that even though our heat and work transfer is going to not be a state function, the sum of heat and work, as long as my end points and starting points are the same, I have the same energy change for the system. Okay, in section 5, we're going to talk about reversible adiabatic expansion for an ideal gas. And what we expect, and what we will show explicitly, is that the temperature decreases. Okay? All right, and as long as we're talking about this, I'm going to say reversible adiabatic compression for an ideal gas. We're going to see the temperature go up, right? And that should make sense. Okay? All right, so our goal in this section is to derive an expression that allows us to calculate the final temperature for a system that's done adiabatic expansion or compression. That's one goal for this section. The other goal for this section is that we're going to come up with the functional form that describes the pressure-volume relationship for adiabatic. That is, that curve B. How do we describe it mathematically? All right. So I've skipped some things here. This is just mathematical truths that aren't worth us focusing time on. Okay. All right. So we're going to go and set out to determine our relationship between the initial and final volume and the initial and the final temperature. All right. What we know is that the change in the energy of the system is given by Cv dt, okay? All right, and because we're talking about an adiabatic process, the only change in energy is going to be due to the work. That's minus PdV, all right? This is the same as this then, all right? And we know that because we're talking about ideal gas, we've got nRT over V dV is going to be the same as PdV, okay? All right, so putting that together, what I can say is that Cv T dt is equal to minus nRT over V dV. Okay? All right, now if I want to get a relationship between my volumes, one of the things I see, and the temperatures, I see that I'm going to have to integrate this. All right? So that means I need to get temperature on the same side, all right, and volume on the other side. All right, so I'm going to divide both sides by T. I'm also going to divide both sides by N. All right, so if I divide both sides by N, that's going to get me Cv over N. Whoops, jumped ahead there. Cv over N. And that's the same as our molar heat capacity, right? So heat capacity divided by N is the same as the molar heat capacity, right? So on the left side, I will have the molar heat capacity over T dt. And that in turn is going to be equal to minus R dV over V. Okay? Does that make sense? All right, so now what I'm going to do is I'm going to integrate this. One of the things that we're going to do first is I'm going to say, let's put in a specific heat capacity. And then after that, we're going to generalize this and use a temperature-independent heat capacity, all right, to get a more general relationship. For right now, we're going to say, let's talk about a monoatomic ideal gas. And what we've previously shown is a heat capacity for a monoatomic ideal gas is temperature independent, and it's equal to 3/2 R. Okay? All right, so looking at the left side of the equation, that means I'm going to put in 3/2 R over T, or dt over T. Okay? And I'm going to need to integrate this from my initial to my final temperature. I can choose to put 3/2 R out front, so it'll be T1 to T2, right? That's going to give me 3/2 R. What's the integral of 1 over T? It's a natural log of T. And because my limits are T1 to T2, that will be T2 over T1. Oops, I'm going to change my pen color. All right, does that make sense? All right, so I'm also going to look at the right side of this, right? So what I've got is minus R dV over V. So I've got minus R integral V1, V2, dV over V, right? So that's going to be minus R ln of V. And because we're going from V1 to V2, that's going to be a natural log of V2 over V1. Okay? All right, so that's integrating this side, right? And because these are equal to each other, that means these are equal to each other, right? So I set those equal to each other. What I'm going to do is I'm going to notice I've got R in both sides, right? So that means I can divide through by R, right? So that's going to give me the natural log T2 over T1. Now, if I want this to be, if I don't want 3/2 outside, how do I bring it inside the natural log function? I raise it to the 3/2 power, right? Right? And that in turn is going to be equal to, let's say I want to get rid of this negative sign, right? So if I want to get rid of the negative sign, what happens to my ratio? It flips, right? So that's going to be equal to plus the natural log of V1 over V2, okay? All right, so I chose to do this in this manner because now I've got the natural log of each side. So this means I can take the inverse function or the exponential of both sides, and that's going to get me my relationship between temperature and volume. Does that make sense? So I'll just say E to the this, E to the this is going to yield T2 over T1 to the 3/2 is equal to V1 over V2, right? So for a monoatomic ideal gas, we have derived the expression that tells us the temperature that we're going to end up with upon expansion or compression. Okay? All right, let's take a moment to look at this a little bit. So if I'm talking about expansion, what's the relationship between V1 and V2, assuming I'm starting at V1 and ending at V2? Expansion means who's larger? V2, all right? And therefore, we can say that V1 over V2 is going to be related how to 1? Less than, all right? And if this is less than 1, that means that T2 over T1 also has to be less than 1, all right? So we can say, therefore, T2 over T1 is less than 1, or T2 is less than T1, right? So we've used this equation to prove what we've set out to prove. What we've expected is that when I do a reversible adiabatic expansion, my ideal gas temperature changes and it decreases, right? By the same token, if my volumes were flipped, that means I'm doing a compression. If I'm doing a compression, I expect the temperature to go up, okay? All right, so we're going to do this as a group quiz, and then part as a big group, and then I think I'm going to have you guys finish off part of it on your own for using your brain power. Let's see, I'm going to ask you to pass one behind you, if that's okay. Let's see, what do we got here? We're going to throw 3 this way. Okay? Okay, so let's go ahead and talk this one through. So what we've done is we've come up with an expression that works just for a monoatomic ideal gas. What we want to do is extend that to something more general, right? So in this case, we're going to talk about expansion of an ideal gas, and our heat capacity is just going to be temperature independent C sub V, okay? All right, so starting this one out, we know that du and dw are equal to each other because dq is equal to 0. So minus pdv is going to be minus nRT over v dv. And that in turn is equal to the change in the energy of the system, which is what times dt? CV. All right. Now, because we have a temperature independent one, I'm just going to write this as independent of temperature. So I have CV. Whoops, so I made a mistake. I don't know that I have a mole. All right. So that means I have to have a general heat capacity. All right. Now, I want to collect the terms again. So I'm going to divide both sides by, help me out, what do I divide both sides by? N times T. All right. And the result of that will be minus R dV over V is equal to CV over T, molar heat capacity now, dt. Right? Now I have something that I can integrate. Right? So R is a constant, so I can choose to put my integral out in front, or R in front of the integral, and then CV, CV is independent of temperature. We can pull that out front. Well, we'll pull it out in front later. So it'll be T1 to T2, V1 to V2. Okay? All right, looking at the left side, this is going to get me minus R. What's the integral of 1 over V with respect to V? ln V2, V1. That's equal to plus R ln, who's on top? V1 over V2. All right, so that's my left side integral, all right? And that in turn, my right side integral is going to be the integral of 1 over T, which is the ln of T2 over T1, right? And then I have my molar heat capacity out front, okay? All right, so I'm going to write that's equal to CV ln T2 over T1. Right? Now we need to get rid of the natural log function. And so here I'm going to step back and I say, all right, I want T2 over T1 to some power. So that means it's going to be related to R and the heat capacity. So I need the heat capacity and R on the same side as the temperature. All right? So I can say that ln V1 over V2 is now equal to CV over R ln T2 over T1, okay? All right, because I need to take the anti-log, or the inverse function, I'm going to choose to put T2 over T1 to the power of CV over R, okay? Now I can take the exponential of both sides, and what we end up with is V1 over V2 is equal to T2 over T1 to the molar heat capacity over R, right? And if you think back to what we've just derived, for a monoatomic ideal gas, the molar heat capacity is 3/2 R. So 3/2 R over R, that's 3/2. That's what we've derived. Does that make sense? Okay. All right, so let's put that aside for now. Let's go back. All right. Okay, so the next thing that we want to do, and you want to pay attention to what I'm doing here because I'm going to let you guys do this part on your own, all right? All right, so I want to get a function that describes the pressure-volume relationship. What I know at this point is that T2 over T1 to the 3/2 is V1 over V2. Because I have an ideal gas, I can say, well, I know that the temperature is going to be equal to the initial pressure volume, or PI, VI, over NR, all right? So I'm going to be able to substitute in this expression in the numerator, this expression in the denominator, and we're not changing the number of moles, so that means that NR is going to go away, okay? All right, so putting that together, in the numerator, I've got P2 V2 over NR. That whole thing is divided by P1 V1 over NR, right? That in turn is raised to 3/2 power, and we see that this ends up as P2 V2 over P1 V1. So that's P2 V2 over P1 V1, and that's the same as V1 over V2, right? So I want to get, whoops, and I left one thing out. What did I leave out? My 3/2. All right? Now I want to get P2 V2 on one side and P1 V1 on the other side. So that means that I'm going to be able to I'm going to multiply both sides by P1 V1 and V2, right? To make the arithmetic a little bit simpler, I think I want to get rid of this 3/2. So what would I raise both sides to? 2/3. So that will get me P2 V2 over P1 V1 is equal to V1 over V2 to the 2/3, right? And now I can multiply both sides by P1 V1 and both sides by V2 to the 2/3. So that's going to get me on the left side P2 V2, right? So this is V2 to the 2/3, and this is V2 to the 1, which is 3/3. So it's going to be P2 V2 to the 5/3. And that's equal to P1 V1 to the 5/3. Okay? Right? And that's the constant, right? So for a monoatomic ideal gas undergoing adiabatic expansion, this gives me the function that describes that curve. Okay? All right, and that's clearly different than the isothermal expansion, which was P1 V1, or PV equals a constant. Okay? All right. All right, so if I talk about an ideal diatomic gas that has no vibrational contribution to the heat capacity, we've previously shown that that molar heat capacity is 5/2 R. All right? And so what we can do is go back to what we've just shown on our quiz and say that T2 over T1 is equal to V1 over V2, right? And I didn't remember off the top of my head, it's CV over R, right? So 5/2 R over R becomes 5/2. Okay, so there we have the relationship between temperature for initial and final volumes for adiabatic expansion, now a diatomic gas, right? And these are different because we have different heat capacities, right? So this is where I'd like you to take 2 minutes, right? And we do need to limit it, right? And I would like you to work as in your team to determine the expression P1 V1 equals P2 V2 to the what power for this generic case where we have a temperature independent heat capacity. So we've just done this explicitly for a monoatomic ideal gas. So I've replaced 3/2 R with CV. Okay? And I think that I'm going to start a 3-minute timer. Yeah. Yeah, you can do it on the back. If you left room on the front, you can do it on the front. Just do it. Yes. No, you're going to do it generic. So it's for CV. Okay? You still need to do that substitute in for the temperature, PV over NR, right? And that will get you your ratio of PV. But it's going to be to the CV over R, right? You're about halfway there. You have 20 seconds. All right, time is up. Wherever you are, it is time to stop. Melissa, you have to be mean today. I'm mean every day. Thank you. Thank you. All right, so I also wanted to just mention, did we get yours? Thanks. Everybody? Okay. Thank you. Okay. All right, it looks like, whoa, sorry. I should probably pay attention to where I'm walking. All right, so one thing that I wanted to point out, this what we've just done is exactly the same question as homework 9, number 5. So you can't complain about number 5 on the homework that's due next week. Well, I guess you can, but we've just done it. Okay? All right, so we can take the equation that you guys just derived, and for a diatomic ideal gas, what we find is that our relationship is P1 V1 to the 7/5 is equal to P2 V2 to the 7/5. Okay? And that was 1 plus R over CV is what that relationship came out to be, generally. All right, so we've been working pretty abstractly, so I wanted to take a moment to just do a quick calculation. I want to point out in the textbook, example 5.5 does exactly the same volume change, same initial temperature for a monoatomic ideal gas. We're going to ask what's the final temperature for a nitrogen. We're assuming it's ideal at an initial temperature of 300, right? Okay, all right, so we're interested in T2, right? And so that means we're going to have to take both sides of the equation to the 2/5. So that's going to be V1 over V2 to the 2/5 times T1, right? We plug in our initial volume, 50 liters, final volume, 200 liters. Liters cancel, raise that to the 2/5, and then multiply that by our initial temperature, which is 300 Kelvin. And we find that our final temperature is 172 K. Right? So I did want to take a moment and just mention this is different than for a monoatomic ideal gas. And that's because they have different heat capacities. Right? And what we see is that for monoatomic ideal gas, we have a lower heat capacity, which results in a greater temperature change. We're going from 300 to 119 versus 300 to 172. So I wanted to take a moment to look at what that does to a pressure-volume curve. So I've got pressure on this axis. I've got volume on this axis. I'm going to draw in an isotherm. We're going to have the same initial volume, same final volume, right? So for one of my gases, I end up at that final pressure. And for my other gas, I end up at that final pressure. Okay? All right. So if we think about it, we have all these gases, same number of moles, right? The only difference is the pressure, and that's due to the temperature. All right? So this corresponds to the monoatomic or the diatomic. Which one went to a lower temperature? Monoatomic. All right? So that's our monoatomic. And our diatomic is this one. All right? And we also see that there's a difference in work that occurs. So isothermal expansion gives us the most amount of work, then my diatomic, and then my monoatomic, right? So as the heat capacity gets smaller, I have a greater temperature change, and I've reduced work, right? That's where we're going to leave it for today. I did not go over. I was worried about that. Okay. All right. I won't see you on Friday, but Brian will. Have a good day. See some of you in office hours today or tomorrow. And our guests today, you can tell them how awesome it is to be chemistry majors and how awesome it is to be chemical engineering majors. And biochemistry's all right, too. So, did I leave anybody out? No. All right. So thank you. You didn't fall asleep. Yeah.
Thank you so much.
Yep. So, are you guys visiting this Saturday for a Science Bomb Saturday? So we're doing a chemistry session at 9:30 to 11. So if you want to sign up for that, it'd be good to see you. Okay. Yep. Hi, Melissa. How are you?
I'm okay. Okay. So I.